Good morning, folks. Welcome back. Our goal today is to start talking about functions, which are a really core part of the course. And if you look over the topics we're going to cover for the rest of this week and then also next week, it's all various stuff related to functions. And again, this is stuff that's going to show up in lots of different places in other courses that you take, because this idea of being a function is pretty central to a lot of areas of mathematics. I did, when I was looking over the homework and some of the questions, realize I meant to add a part to question 58, and I added it to the end of 60. So if you look at 60F on the homework, you'll realize it doesn't have anything to do with anything else in question 60. It's because I meant to add it to the end of 58. Sorry about that. All right. So to start with, I want to go over people's questions, and then I'll do some examples of a variety of types of things as usual, and leave options for you to talk about or ask about whatever you like. Okay. So, first question I have here is, what's the difference between the codomain and the image? So, this isn't a great question. So, when I write down a function, the b that I put here, this just is the codomain. Okay. And sometimes it's also called the target, which if you think of functions as fundamentally being this like set of arrows that are originating in A and landing in B, B is the target. It's where all the arrows are landing. However, remember when we write down functions, as per our pictures, it is not obligated that we use all the elements of B. The elements of B are just there as options, things that could be used as outputs. And so the image is the things that are actually used. So this whole thing is the codomain in this picture, whereas the image is just these 2 points. And so maybe the statement to make this the clearest is that the image is by definition a subset of the codomain, but it might not be all of the codomain. Okay. And so if, for example, I took this function from R to R that takes x to sine of x, the image of f here is the closed interval from -1 to 1, but the codomain of f is all real numbers. Okay. And so 2 is an example of an element that is in the codomain. Why is it in the codomain? Because I wrote it that way. But 2 is not in the image because there's no number whose sign is 2. Okay. Any questions about that? I know this distinction is a little weird, and it's a little weird particularly because we don't have this distinction between the domain and something else, because with the domain, we're just obligated to use every element. Okay, so the question from the chat is, why wouldn't we just write this as g goes from r to minus 1, 1, that takes x to sine of x? And there is no particular reason why you would prefer this to this. They're both perfectly acceptable functions. And in a lot of ways, these look like the same function, but they're not quite the same function because of the different codomain. But the observation here that underlies this is correct, which is that you could always replace the codomain with the image and get a valid function. It'll just be a different function. Now, there's maybe a lurking, well, why do we even let the codomain be bigger than the image sort of question under this? And I think an example where you sort of see why that's the case is that if I write down something like this, the image of this function is sort of annoying to describe. Because the image of this is just the numbers in z plus that are factorials. And if I tried to write this down, it would look really ugly if I had to write this as to the set of n in z plus such that there exists m in z plus such that n is m factorial that takes some number n to n factorial or whatever. And so this is just an uglier thing to write down than this. And so that's why we have this problem. Often, by the way, as I noted in the video, there's plenty of functions where we just can't calculate the image, or we just have no idea what the image is, or we only know what the image is with great difficulty. So that will also be part of it, is that often you cannot calculate the image, but you definitely know that the image is a subset of something in particular. So if I were to write down, let's say, I can be certain I've written down a valid function here. But if you were to actually try and calculate the image of this function, it would actually take you some effort. You could do it, probably, but it would take some time. Okay, so there are also questions about functions from the empty set. Okay. So ultimately, maybe it makes sense to first start with, what does it mean to write down a function from a finite set? So let's say I were to write down f from the set 1, 2, 3 to the real numbers. There's a few different ways I could do this, but probably the easiest way is to provide a list of each element of f and where those elements map. And so note, here I've completely described a function from the set 1, 2, 3 to the reals. Okay. I've just said, okay, where does 1 go, where does 2 go, where does 3 go? And so that's a function goes to the real numbers. Okay. And in fact, every function from 1, 2, 3 to the real numbers I could get by writing down, okay, where does 1 go, where does 2 go, where does 3 go, and I just need to fill in each blank. And pick whatever real number you like for each of these slots. You could even pick the same real number for all of the slots, and that will give you a different function from the set 1, 2, 3 to the reals. So, following this idea, I could ask something like, how many functions are there from the set 17 to the set 1, 2, 3, 4, 5? And so, to do this, I actually literally only need to tell you where 17 goes, right? I just need to give you a list of, okay, where does 17 go? And I could pick any of 1, 2, 3, 4, or 5. And those would each give me a different function that goes from the set 17 to the set 1, 2, 3, 4, 5. And so there are a total of 5 functions from the set 17 to the set 1, 2, 3, 4, 5. Okay, so the thing that was asked about was then, okay, well, what about functions from the empty set to the set 1, 2, 3, 4, 5? Okay. And so in order to give a function from the empty set, what do I have to do? Well, I just have to specify where every element of the empty set goes. Okay. And this box that contains nothing contains a description of where every element of the empty set goes. Now, it's a little weird that this box has described something about every element of the empty set, even though it's empty, but that's kind of the whole point of the empty set, is that there isn't anything in it. So if I want to describe something for every element of the empty set, I'm done as soon as I've written nothing. And so the heart of this is that this is the only function from the empty set to the set 1, 2, 3, 4, 5. And this is the only function, but this is in fact a function from the empty set to the set 1, 2, 3, 4, 5. And so you should be careful of this. So there's, in fact, exactly one function from the empty set to any one particular set that you would like. Someone asks if it is possible for the Cartesian product to be the codomain of a function. And absolutely, the codomain of a function can be a Cartesian product. So here's an example of a function where the codomain is the Cartesian product of something. I could take something f from R to R cross R. Takes t to t squared t cubed. And so, for example, if you were to take f of 5, it would give you the ordered pair 25, 125. And if you were to like sketch a graph of this, it would end up looking like that. And by sketch a graph of this, what I really mean is sketch a graph of the image of this function. Okay, someone asks, when I say a function is non-constant, what does it mean? So let me first say what a constant function is. Okay, so this is what it means to be constant. It means there's a single output that every element of the input takes. So in Calc 1, a constant function is one whose graph is a horizontal line. So say y equals 3, for example, where every input is just giving me the output 3. But that works for any particular any type of function. All it means is there's only one output. The reason, by the way, that I specified non-constant in question 57, which asks you for examples of functions, and it asks you in particular for examples of non-constant functions, is that if I did not specify that, you could just give me basically a list of a constant function for every question. So you could just say, okay, for 57a, I'm going to send every element to 1/2. For 57b, I'm going to send every element to 1/2. For 57c, I'm going to send every element to 1/2. And so on. And that would not really get at the heart of what's going on. So I want you to give me like marginally more interesting examples than that. Someone asks how I know what the natural domain of these various functions is quickly. So I believe this is alluding to the fact that in the video I say something like, okay, this is the natural domain of sine and cosine and these polynomials and irrational functions and etc. And that's basically because when I was being taught pre-calculus and calculus, they made us like memorize all of these facts about all of the trig functions and all of the graphs and these sorts of things. And so my brain sort of like when someone says e to the x, I like instantly know what the graph is and what the domain and codomain are, and all of these sorts of things. People have drifted away from that, I think, much for the better. So you may be in a different position where if someone says e to the x, you might have to think about it or pull out a calculator or whatever to picture exactly what the graph looks like and see these sorts of things. So I think this is a shift in how people teach the various functions and that kind of thing. So certainly if you wrote down like a really random looking function, I would not know these things. But for something like sine, cosine, tangent, it's just sort of something that was I was made to memorize. Okay, so there's also a question about these arrows, and it's worth talking about these arrows. So someone asks, if I have f from some set, let's say a to b, is that the same as f of a equals b? And the answer is no. These are different things. But if I say that f takes little a to little b, that is the same as saying f of a is b. Okay. And so in particular, if I wrote that f in fact takes a to b, when I use this maps to arrow, again, this should be read as maps to, and that's also the LaTeX for this arrow. This would mean the same as f of a equals b, but this would be incredibly confusing. Okay. And why is it incredibly confusing? It's incredibly confusing because this looks suspiciously like I'm describing a function whose domain is A and codomain is B, and I've used the wrong arrow. And so I would never write something like this because of that. Because what this is really saying is there's a function whose domain and codomain I have not necessarily specified, but whose domain contains the set A as an element, and whose codomain contains the set B as an element, and it takes the set A to the set B. So generally, I would just don't write this. That is basically what I am saying. But the key thing here is to really take away this arrow with no vertical line is telling you the domain and codomain of a function. So when you see this arrow, it is domain on this side, codomain on the other side. Whereas when you see this arrow, it is telling you the input on one side and the output on the other side. So just to go back to our earlier example, when I was writing down this, we had the set 1, 2, 3 was the domain. That was being mapped to R as the codomain. And then each element, I specified where it went. And when I was talking about individual elements of the domain, I specified their inputs and outputs using the maps to arrow. Are there questions about that? I know this notational distinction feels weird at first because you're not used to thinking about this relationship, because writing down the domains and codomains of a function is pretty new. But is there anything I can say to sort of clarify this, or any questions about that? Is there a name for the domain-codomain statement? If there is, I do not know what it is, although admittedly there are lots of names for things that are random Latin things that I do not know. Like, I think I saw someone talking about what the mantissa of an integral was the other day, and I did not know that that had a name. But yeah, if there is a name, I do not know. But just remember, here's an important thing. If I specify this, I have not told you a function. And in the same way, if I wrote this, I've still not told you a function. I've also not specified a function. Okay, in order to specify a function, I need to describe all of the domain, the codomain, and the map in order to completely describe a function. Okay, so there's some questions from the homework. So let me grab some questions from the homework. So it's like 54, 57, 58, 59, 60. 54, 57, 58, 59, 60. Oh, by the way, this reminds me, I should officially say, I don't think I've officially said what I'm planning to do with the class starting next week. So next week we're going to be back on campus. So my plan is to continue posting all of the lectures to YouTube in the way that I have, so that if you're in quarantine or whatever, you can still have full access to them and you can review them because you've probably gotten rather used to that. But I will shift doing this section. I'll still have you submit the questions on Katie, but I'll shift this part to where I answer the questions, talk about them, and give you some questions back. I'll shift that to where we meet in the classroom, and so you can come and ask questions there, and so forth. So that's basically my plan, is to keep the class sort of as stable as possible in terms of how we're doing things, and just do this in person. And that way, if you miss, you can still talk to me in office hours or afterwards or whatever. And that will be a good way to make sure that you don't miss too much. Okay, so let's talk about these questions from the homework. See, so 54 asked, is it true that if A and B are sets, then the power set of A minus B is the power set of A minus the power set of B? Okay, and to be clear, this is a prove or disprove. And so as it would happen, this statement is false. And so in order to disprove it, we need to find a counterexample. That is, I need to find sets A and B where this statement is false. And there's a very fortunate fact, which is that, in fact, every possible choice of sets A and B is a counterexample to this. But I'll choose maybe some reasonable examples. So the power set of A minus B in this case, well, A minus B is just the set 1. So the power set of A minus B is just the empty set and the set 1. Whereas the power set of A minus the power set of B, well, that's the power set of A, I'll just write down, minus the power set of B, which is the empty set and the set 2. And so what is this difference? This difference is the set 1 and the set 1, 2. And this is a counterexample because these two things are not the same. Now, out loud, I just made a quite strong claim, which I did not ask you on the homework, but I actually made the claim that, in fact, not only is this not true, but that it's actually not true for every pair of set A and B. Can anyone in the chat give me a 2-word description of why this is actually never true, that the power set of A minus B is equal to the power set of A minus the power set of B? Empty set. Yes, that is the 2 words I had in mind. So here's how I know this is not going to be true if I think about it. It's definitely true that the empty set for every set AB, the empty set is always an element of the power set of A minus B. It's also always an element of the power set of A, and it's always an element of the power set of B. And why is that? Well, the empty set is an element of the power set of every set. So in particular, it's an element of all of these power sets. But this means in particular that the empty set is not an element of the power set of A minus the power set of B. Because the empty set is in both the power set of A and the power set of B. And so that means that it can never be the case that the power set of A minus B is equal to the power set of A minus the power set of B, because one of them contains the empty set and one of them does not. Now, please note again, you did not need to write anything like this on the homework. In fact, for the homework, all you had to do was write one example, because the homework asked you to disprove a for every statement, so you could do that with an example. But I am just showing you that, in fact, actually, this never works. Okay, let's see, 57. So I'll do a bunch of examples like 57 when I get to my examples. So I will hold off on talking about 57 until I do my examples. Ditto 58. I will also do examples like 58 in a minute. So I think once you see how to do 58, you will also be happy with how to do 59. 59, I will tell you just in advance, 59's proof will be a proof by cases. And then for 60, let's write down the definition and let's make sure we understand what the pre-image is. So the setup for this definition is that I have a function f from A to B, and I've chosen some subset B prime of B. And this prime, by the way, has no significance other than to say, like, this is some set that's in some way related to B. So the prime is just saying it's some other set. I could have called it C if you'd have preferred, or whatever. The prime certainly doesn't have any special meaning. Okay, then we define this thing that we call the inverse image under f of B prime. It's defined to be the set of A in A such that f of A is an element of B prime. Okay, so this is just the notation. This is the inverse image of B prime. Okay, so let's do an example of coming up with the inverse image of something. So let's take f going from R to R. It takes x to x squared. And let's ask, what is the inverse image of the closed interval 1, 4? Okay, well, let's just spell this out. Okay, so f inverse of the closed interval 1, 4 is the set of A in R such that x squared is in the interval 1, 4. Okay, and what numbers here am I describing? Well, what numbers square to something between 1 and 4? Oh, did I call it pre-image in the question? Sorry, inverse image and pre-image are the same word. I used a different word in the... Yeah, so inverse image, pre-image. Sorry, my bad. So in this case, I'm asking, what are all the things I can square to get a number between 1 and 4? And the answer is a number between 1 and 2, but also a number between -2 and -1. Okay, but these are all the numbers that I can square to get something in 1, 4. Questions about that? Okay, so let me give you some examples of things like these various questions. So let's start with stuff. Actually, before I get there, let me ask, and let me just give you a little bit of practice. And so I'll give you a minute to think about these. So what I want to know is, what are the natural domains and images of these functions? Okay, and so I will pick secant of x and 1 over the square root of x. So I'll give you just a handful of minutes to think about these and think about what the natural domains of these functions are and what their images are. Okay, so let's talk about... I'm actually going to do the second one first. So what's the natural domain of 1 over the square root of x? R plus, right. In order to take a square root, I need the number to be at least as big as 0. But then 0 does not work because 0 also makes the denominator 0, which will not work. So I can't divide by 0. And so that means at the end of the day, I get the positive real numbers. That is my domain, which you might also want to write as 0, infinity, whichever way you prefer. Okay. So what is the image of this function? It's perfectly allowable, by the way, to pull up a graph of this function as part of answering this question, if you are not sure off the top of your head. And now, all at once, everyone agrees. R plus. Yes, this is also R plus, right? The image of this function is R plus. Namely, I can get out every positive real number from this function. Okay. So what about secant? What is its natural domain? Or maybe a better question, what are points where secant is undefined? So, like, can anyone give me a point where secant is undefined? Yeah, so there's pi over 2, right? Because remember, secant is 1 over cosine of x. So everywhere that cosine is 0, secant is undefined. And so then this becomes the question of where is cosine 0? And cosine is 0 at pi over 2 and 3 pi over 2. But then, annoyingly, also at these other points. So it's also at 5 pi over 2 and 7 pi over 2. But then the other direction as well, at negative pi over 2 and negative 3 pi over 2, and so on. And so if you go to write down what this set is for the domain, keep in mind it's the complement of this set of points where it's undefined. So it is going to be R minus the set of, and so this is pi over 2 plus pi k for k in z, as May suggests. So this is, as it happens, the natural domain for secant. Okay. Namely, it is all the in-between spots where secant's not undefined. Can we write it as the set of x and r where cosine of x is not equal to 0? I mean, it's completely right. I'm not sure it's super helpful if you need to know the... I'm not sure it's super helpful if you need to know the codomain in this sort of explicit way. But I think it is... but it's not wrong. So I don't think I could complain about it. Okay, so what's the image? Again, unless you have also memorized the graph of secant, you will probably have to look at a graph or think about this for a second to come up with what the image of this function is. I don't think it is all of R. Is 0 in the image? There we go. So the image here is actually minus infinity to minus 1 union 1 to infinity. Okay. And so what's happening here is that if you look at the graph, it's got these things that look like parabola shapes embracing the vertical asymptotes. But actually, if you were to just draw in the graph of cosine would actually draw in like this. And so, in fact, actually, the graph of cosine just kisses the graph of secant at each of these, at the vertex of each of these things that looks kind of like a parabola. And so what that means is this whole middle part between minus 1 and 1 is not a valid output of secant. I can't get in between minus 1 and 1. Okay. Again, I think that's really hard to think through if you don't look at a graph. You certainly can think through it, but it would take a little longer. But if you look at a graph, you should be able to see there's this sort of like no man's zone in the middle where there's no inputs that give you an output that is there. Okay, so speaking of questions about the image, I'll ask, is 5 in the image of, and I'll write down the function from R to R, takes x to x squared plus x plus 1. How about minus 2? Okay, let me give you a few minutes to think about this and make sure we're sort of getting comfortable with this idea of what image means, at least for these sort of functions that look calculus-y. And then we'll do some more examples from functions that are not as calculus-y. But I'll give you a few minutes to think about this first. Okay, so let's start with 5. So when I ask if 5 is in the image, what am I really asking? I'm really asking, does the equation f of x equals 5 have a solution? Okay. So that really translates to asking me to solve the equation x squared plus x plus 1 equals 5, which if I then do my usual algebra thing, that'll give me x squared plus x minus 4 equals 0. Now, as it happens, this does not factor in some nice way, but we do have the quadratic formula to help us. So I could take x equals minus 1 plus or minus the square root of b squared minus 4 times 4, so that will be 1, and that'll be plus 16. And then over 2, And so, because this is a real number, and because the quadratic formula always gives us roots if the thing has a root, that tells me that yes, 5 is in the image. And it's in the image because f of one of these numbers is 5. And so we're getting away with less work than we might in some other instances because we have the quadratic formula here. And the quadratic formula, and in particularly, because the quadratic formula, and in particular the discriminant of the quadratic formula, tell us exactly whether the polynomial we get has a root or not, which then tells us whether or not this thing is going to be in the image. And so then we could ask a similar question. Does f of x equals minus 2 have a solution? Okay, and then we can do the same thing. So we'll get x squared plus x plus 1 equals minus 2. And so we're now looking at this. Uh, 1 minus 12 over 2, which is minus 1 plus or minus the square root of minus 11. This is not a real number. So since this equation has no real solutions, that tells me that negative 2 is not in the image. Okay, are there questions about this in particular before we go onward to talk about what the image actually is? In the analogous question, by the way, on the homework, I say something like prove carefully that, or prove your answer carefully. What I'm saying there is just like make sure you don't just tell me yes or no. Tell me why. And so if something is in the image, you should probably be able to give me an element in the domain that maps to it. And if it's not in the image, you should be able to prove to me that no such thing exists. Okay, so for this function specifically, we're going to be able to write down its actual image because we know what the graph of this thing looks like, right? Namely, the graph of this function is a parabola. And really, there's only so many things to know about the graph of a parabola, namely the vertex and whether it points up or down. And so here we basically get to turn this into a pre-calculus question. So this parabola points up because the coefficient out front is positive. And the vertex, which is given by this negative b over 2 formula, is at x equals negative b over 2a, which is minus 1/2 in this instance. By the way, now that you've had calculus, you don't really need to remember the vertex formula anymore because the vertex is the place on the parabola where the derivative is 0. So you can sort of rederive that every time you need it because you probably don't have a hard time taking the derivative of x squared plus x plus 1. So the vertex here is in fact actually minus 1/2, comma, and then let's see, what is the y coordinate here? So it'll be 1/4 minus 1/2. It's minus 1/4 plus 1 is 5/4. And so the graph here, there's my vertex. Here's the parabola that points up. So if you believe my work there, what is the image of this function? Yep, so the closed interval from 5/4 up to infinity. Namely, all the y's that start here at 5/4 and go up. Okay, and that's something I know, again, because I'm lucky that I have the graph in front of me. And I'm lucky that I have years of algebra experience to know that this is a parabola, so I know what the graph looks like. And once you know what the graph looks like, the image is free. Okay. This is an excellent point to remind you that notation is sometimes ambiguous. So this is an ordered pair. Okay. But we have plenty of times today, and in fact, literally on the other side of the page, used exactly the same notation to mean an interval. And so you should be careful to make sure you always know whether something being written down is an ordered pair or an interval, because these are very different things. And it is going to be very confusing if you're not sure which it is they're talking about when you're looking at something. Continuing on the theme of calculusy stuff for just a moment, I wanted to show you one particular thing that shows up a lot. So you might be asked something like, is 0 in the image of this function? Sorry, I have now forgotten what I wanted. Plus x minus 1. And so here I'm writing this down just to show you the answer here is yes, but also one can prove you can't write down something that is a 0 of this polynomial. So the answer here is yes, but you cannot possibly prove it by giving an example. And so that sort of asks the interesting question, okay, well then how do you prove it? And the answer is by using this thing that you might recall from calculus called the intermediate value theorem. One way of stating of which is that if a continuous function on all of R takes two values, then it takes all the values in between. And so here what I'm remarking is if I take f of 0, I get minus 1. If I take f of 1, then I get 1. And so if I think about what that looks like in terms of the graph, here at 0, it's down here at minus 1. And then here at 1, it's up here at 1. Basically, what the intermediate value theorem is saying is that if I'm going to connect these two, it's not possible to connect these 2 points without happening to cross the axis somewhere. And wherever I happen to cross the axis, then it takes the value 0, and that proves to me that 0 is in the image. Okay. And in fact, every number between minus 1 and 1 is in the image. I bring this up not because I'm going to ask you anything about the intermediate value theorem, because I certainly can't, because we definitely have not defined what it means for a function to be continuous, but to point out that most of the functions and most of the reasoning you've done with functions in your life about real-valued functions has had the assumption underlying it that the function was continuous or differentiable or all of these sorts of things, whereas we have definitely not had any assumption like that in our definition of function. So if you want to talk about these kind of ideas and you want to draw graphs that look like this and use that kind of reasoning, that's going to require a whole extra layer of structure on top of what we've been talking about in this course. And so, in fact, actually, if you're interested in this, this is our 454, so our real analysis course, is the course that takes care of explaining how all of these pieces actually end up fitting together into the larger puzzle. That is, how do you go from just the definition of a function to the idea of real numbers and the idea of continuity and the idea of proving theorems like this from that. Which turns out to be a really interesting story and one that mathematicians did not understand until surprisingly late in history. So again, I think that's a really interesting story and a really interesting course, but I'm not going to talk about continuity again, I do not think, in this course. So really, that was all a prelude to me talking about functions that don't have the real numbers as their domain or codomain. And so let's take, for example, this question. So I want to give you a couple minutes to think about this, and we'll talk about it together. But this is the structure of question number 58 on the homework. All the questions under this are asking, here's a function I've described for you. Here's a particular element of the codomain. Is it in the image, yes or no? Okay, in other words, is it possible to get the value 1 out of this function? Okay, and I'll give you just a little bit to think about that before we talk about it. Okay, so before I ask the answer to this question, I want to ask a different question. Why is there a plus here? That's exactly right. If I did not insist that this be positive, then I would be allowing for negative exponents. When I look down at where this goes, this ends up going to the I variable, which then ends up in an exponent. And if I took 2 to a negative power, suddenly I might get something like a half or an eighth. And then this thing wouldn't be an integer, which would mean I'd have to change the codomain, which presumably I did not want to do. So there's a lot of care that's taken when you write down a function like this, that you have to make sure that your domain and codomain actually match. Which is not, again, to say that everything in your codomain has to work out. It's possible there are things in the codomain that you do not end up using. However, it definitely has to be the case that everything you use as an output has to be in the codomain. If you did just forget this plus, this would not even be describing a function. Okay, so that said, is 1 in the image of this function? Yes, and so what do I have to do in order to prove that that 1 is in the image of this function? I have to give you an element of the domain that maps to it. What's an element of the domain that maps to 1? Right, f of 4 minus 3 is 2 to the 4th minus 3 times 5, and that is 1. Okay. And that is nice. So if you play the what do I hope the answer is game with the is this in the image questions, you definitely hope the answer is yes, that it is in the image, because if it is in the image, you can almost always get away with just writing down something that happens to map to it. And even if it takes you a bit of work to find the thing, at least you don't have to write much explanation in your LaTeX file for why that is, because once you have the point that maps to it, well, that's all you really need to know. Now, as you might predict, showing something's not in the image is usually going to be more difficult. So, for example, 5 is not in the image of this function, but I think that's a little bit trickier to prove. Okay, so let's now look at giving some examples of non-constant, non-piecewise functions between two particular sets. Okay, and I promise, aside from asking this question on the homework and possibly an exam, you will never again hear me say the phrase none piecewise. just to emphasize, piecewise functions are just as much functions as other things. I was just trying to make sure you actually wrote something for the question for this. Okay, so let's let A here be the set of odd integers. And let's let B be the set of even integers. So I want to write down, an A to B, take N to... and so does anyone have a proposal of where I could take an odd integer to give me a function from the odd integers to the even integers? So like, where could I take N? To N. Great. And so what's the key thing here? The key thing about this 2n is that it is definitely even. Okay, again, because my codomain here is the set of even integers, I want to make positively sure that the thing I put as an output here is really in the even integers. Okay. Here's another example that would work also. And so this is an equally valid answer. Again, if I take an even number and I add one to, if I take an odd number and I add one to it, I definitely get an even number. And so this again takes me from an odd integer to an even integer. So let's go ahead and pause while we look at these two examples and make sure we're sort of happy with them. What are the images of f and g? I'll give you a moment to think about this. So let's start with G. What's the image of G? Right, the image of G is just the set of even integers. Okay, so this is B. Every even integer is one more than an odd integer. And so here the image is as large as it could possibly be, right? I'm looking at a function from the set of odd integers to even integers. And so the image has to be a subset of the set of even integers, and in this case, it's the subset that is all of the even integers. The image of f, though, is what about 0? 0 is minus 1 plus 1. So 0 is in the image. Remember, 0 is even. I will foreshadow that next week we're going to give a name to functions like g, where the image is actually the entire codomain. We're going to call those functions on2, and that's going to be like a whole video lecture, all that kind of thing. So we're going to talk about that a lot next week. But for now, let's hop and talk about f. The image of f definitely isn't b. Can anyone think of a nice way to describe the image of f? I'm not looking for a formal proof. I'm happy to settle for just a description of the set that works out. All the integers in the 4n plus 2 bucket. That's exactly right. If you go back to the division algorithm way of thinking about things, where sort of every number is one of 4 things mod 4. It's either a multiple of 4, 1 more than a multiple of 4, 2 more than a multiple of 4, or 3 more than a multiple of 4. Well, if I'm looking at even integers, it's definitely not in one of those 2 buckets. But if I just look at enough outputs, I pretty quickly stumble upon the fact that all of the outputs live in this bucket. So this is the set of 4k plus 2, where k is in z. And let me write you up a formal proof of that, just so that you can have an example laying around of sort of like what a formal proof that the image of a function is something looks like. Okay, so the claim here is that the image of f is the set of 4k plus 2, where k is in z. Okay. And note in particular, the claim here that I'm proving is an equality of sets. And so what that means is that in order to prove it, I'm going to need to show mutual inclusion. I will someday spell proceed correctly the first try. So let's first show that the image is a subset of this set. Okay, so let's suppose y is in the image of f. Okay. I need to show y is also in this set. Okay. And so here's where we get to play our usual game of unwinding definitions. What does y is in the image of f mean? Y is in the image of f. That means that there exists x in the set of odd integers such that y is f of x. That's just the definition of being in the image. Okay. Now, that means x is odd, and so I can use my definition of x being odd. And so then when I write down what f of x is now 2x, which is 2 times 2a plus 1, which is 4a plus 2. Okay. And this is where I discover that actually the thing I wanted to show was that this thing looked like 4k plus 2, and I showed that it's 4a plus 2. And so then I can go back in my LaTeX file and actually say, okay, this a, I actually wanted it to be k. I probably would not have guessed going forward that that was going to be the thing I needed, but there we go. Okay, and so what have I shown? I've shown you that y, that I supposed was in the image of f, is actually in this set. Okay, so we can go the other direction too. Okay, so we'll suppose B is in this set. So there exists an A. In Z, such that B is 2A plus 1. That's not right. Read the set, Tommy. There exists a B in this set such that B is 4A plus 2. There we go. Okay. But now, looking up at my proof for the other direction, I have a pretty good guess what I'm supposed to do. I'm supposed to say, aha, this is 2 times 2A plus 1. And so if I let, say, little o equal 2A plus 1, then little o is definitely odd because of its shape, almost by definition. And f of o is 2o is 2 times 2a plus 1 is 4a plus 2, which, lo and behold, is B. And so I've now shown that an arbitrary B that's an element of this set is, in fact, in the image, and so we're done. You may note the fact that these proofs are a little involved is why there aren't a ton of questions on the homework where I ask you to prove that the image is exactly equal to something. Because if you want to prove the image is exactly equal to something, you really need to do a mutual inclusion proof, like we just did. And those are usually a little involved. Okay, so any questions about that before we do more examples of writing down examples of functions between two given sets? Okay, so here are three more questions. And again, the question is the same. Here's a set A and a set B. What I want is a non-constant, non-piecewise function from A to B for each of these. Okay. And I'll give you, let's say, 5 minutes to think about this, and then we'll come back and we'll talk about it. Alrighty. So let's look at these. So they involve our new friends, power sets and Cartesian products. And so we have to figure out how we're going to use power sets and Cartesian products in order to get things where they're supposed to go. So let's start with the first one, uncreatively. Although I guess I have not done that mostly today, but we'll actually start with the first one. I want to write down a function from R cross R that lands in R minus. And so it's going to take in an element of the Cartesian product. So that's going to look like something like x comma y, where x and y are real numbers. What can I do to x and y to guarantee that I get... Oh, sorry, there's a 1 here that should not be here. What can I do to x and y to guarantee that I get a negative number? Yeah, so Alex suggests 0 times x minus the absolute value of y minus 1. Okay? And it's perfectly fine, by the way, to just write this as minus the absolute value of y minus 1. Okay? Whatever y is, the absolute value of y is positive, or 0. So negative the absolute value of y is negative, or 0. But then this negative 1 here takes care of the possibility that it was actually 0. Remember, 0 is not an element of R minus, so I actually need to make sure I get something strictly negative, and this suggestion by Alex is a great way to accomplish that. Did anyone have other answers to this question? I think for all of these questions, I think there's a lot of different answers that you could come up with. So just one more option, you might have considered something like this, where you use the fact that squaring, like absolute values, makes things positive, so then you can subtract them and know they're negative. Something along those lines. Okay, next up, we have the power set of the numbers from 1 through 5, except we've thrown out the empty set. And we want to send each element of this set to the set 1, 2, 3, 4, 5. So we're going to write down a function here. It goes from the power set of this, except not the empty set. From there to 1, 2, 3, 4, 5. And so here I'm going to start with a set of numbers between 1 and 5. And so, does anyone have any suggestions on what I can do with a non-empty set of numbers between 1 and 5 to get a number between 1 and 5? So again, my thing I'm putting into the function is some set like the set 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 5 is what I wrote down. I should read that. Uh, what number do you want to associate with this set? One. Why 1? Right, so 1 here is the minimum element. It's the smallest element out of this set. And so I could actually do that in general. I can send every set to its minimum element. And as Alex points out in the chat, I would have a problem with the empty set, because the empty set does not have a smallest element. But that's specifically not in the domain, so I don't have to worry about that. So in fact, I could just send every set to its smallest element, and that's good. In this instance, you could just as easily pick the maximum element. I think there's one more thing you might reasonably do other than minimum and maximum. And the other thing I think you might reasonably think to do is to send each set to the size of the set. So that is to say, the number of elements. So this set, for example, would get sent to 3 because it has 3 elements. And so this set is always going to have between 1 and 5 elements. Or sorry, the subset is always going to have between 1 and 5 elements because it's a subset of 1, 2, 3, 4, 5. And so that is also an option. Okay. So this is the spirit of question 57, which is, I think, the question I got the most questions about, was like, what on earth is this asking me to do? And all it's asking you to do is come up with some reasonable way to write down a function from the first set to the second set. All right. Let's wrap up class here for today, but I will hang around and... Oh, sorry. When you're writing your answer, it's fine to write A and B and mean the A and B that I wrote in the homework packet. You do not have to recopy everything that I wrote. So I'm going to pivot over to office hours now. And so if you want to hang around and ask questions about this homework or earlier homework or the test or anything of that sort, just post them in the chat and I will happily answer them. If you want to hang out and lurk and see if anyone else asks an interesting question that you want to see the answer to, you're welcome to do that. If you're happy to run and go get lunch or do whatever things people do at 1 o'clock, by all means, go do that. I will have office hours tomorrow at the usual time, so tomorrow at 11. So if you have more questions that arise as you think through this, by all means, come tomorrow to the office hours. And for Friday, be sure you have watched the video on one-to-one functions before class, because we're going to go over those and some more examples with those, and that will help, I think, prepare you to get a sort of little start on the stuff that's going to sort of creep in next week and start to be the main focus of the test that's coming up the week after that. But for now, have a wonderful afternoon, and I will see you either tomorrow or later today in office hours or on Friday. I can go over number 6 from test 2. Test 2, number 6. Okay, so here we're given our friends the Fibonacci numbers. And we want to prove that for all n and z plus, we have that the nth Fibonacci number is less than 2 to the nth power. Okay. So how is this going to go? So this for all n and z plus is a pretty big hint that this is going to end up being an induction question. But it's going to turn out to be the kind of induction question where we need to modify the inductive hypothesis. Namely, we're going to have here, when we write this down, our base case, I'm going to check that this is true for n equals 1 and n equals 2. One is also less than 4. So I've got my two base cases. And then for my inductive step, I want to write down that if f sub k minus 1 is less than 2 to the k minus 1, and f sub k is less than 2 to the k, then f sub k plus 1 is less than 2 to the k plus 1. And I want this to be true for all k and z plus. So how do I know that this is what I'm going to need to use as my inductive step? How do I know I needed to modify it? And the reason how you know, or the way you know that, is because the definition of Fibonacci numbers is that they satisfy this relation that relates them to the previous two Fibonacci numbers. And so in order for you to prove something about a Fibonacci number, you probably need to prove that it follows not from something about the previous one, which would be the ordinary induction flavor, but that it follows from the previous two. Okay. And so then what does the proof of this inductive step look like? The proof here looks like, suppose we have this k, then I want to consider f sub k plus 1, which is equal to f sub k plus f sub k minus 1, which is then, by assumption, less than or equal to 2 to the k plus 2 to the k minus 1, which, if I keep going, this is equal to 2 times 2 to the k minus 1 plus 2 to the k minus 1, which is 2 plus 1 times 2 to the k minus 1, which is 3 times 2 to the k minus 1, which is what would happen is less than or equal to 4 times 2 to the k minus 1, or sorry, strictly less than. I need strictly less than, but it is strictly less than it. Oh, this was also strict, so this did not need to be strict, but this is strict, and then that is just 2 to the k plus 1. And so that is our proof. There are, by the way, all kinds of different ways that people waded through this inequality. There's not sort of only one way to get from this fact together with these two facts and get here. So, I mean, all I needed for this step to follow is that 3 is less than 4. But why did I want a 4? I wanted a 4 because 4 times 2 to the k minus 1 is what's equal to 2 to the k plus 1. Because 4 is 2 squared. But there was no pre-existing 4. I needed to realize that 4 is what I needed there. Anything else I can help you with? Yes, we can also look at number 5. Number 5 is to prove that this thing is always a multiple of 8. Sorry, n and z, not z plus. This n times n plus 1 times n plus 2 times n plus 3 is divisible by 8. Okay, so this is a proof by cases. So we're going to suppose that n is an integer. And then we're going to break into cases mod 4. So our cases here are going to be that n is 4k, n is 4k plus 1, n is 4k plus 2, and n is 4k plus 3. If I don't break into cases, I don't quite get enough of, or I don't get enough information, and just doing even and odd isn't quite enough information. Although what a lot of people did was to break into even and odd, and then once they'd broken into even and odd, break into an additional case based on that. But that amounts to the same thing as doing this. And so just to walk through what one of these cases looks like, let's take case 2. N is 4k plus 1. What does that give me? So then n times n plus 1 times n plus 2 times n plus 3 is, okay, so this is 4k plus 1 times 4k plus 2 times 4k plus 3 times 4k plus 4. And what I need to notice is that I can factor a 2 out of this and a 4 out of this. And so if I factor a 2 out of this and a 4 out of this, that's going to give me that this is 8 times 4k plus 1 times 2k plus 1 times 4k plus 3 times k plus 1. And in particular, that means this thing is a multiple of 8, which is what I wanted. But if you do this, the other cases work out very similarly. You can always factor out an 8 like this, and so you always end up with this thing as a multiple of 8. One is maybe faith that I'm a nice enough person to not make you do something with 8 cases on a test. But I mean, it will work if you break into cases mod 8. You'll just end up doing more work. But I would actually start the other direction. I would start with try even and odd and realize that if you do even and odd, you don't quite get enough to actually answer the question. So you actually need more than just even and odd. And so then I'd go to 4. I would start with trying to do as few cases as possible and work up instead of the other direction.